Welcome, everyone. For today's prep, we're going to see how we can use calculus to help us find power series representations for more functions, more types of functions here. And the example we're going to look at is similar to that special form, the 1 over 1 minus x that we've looked at now, except it's not quite in that correct format because we have this squared that's around the entire denominator. So what we're going to see is how we can use derivatives and integration to kind of help us deal with that squared. So what are we going to do here? Well, we're going to first of all find the power series representation for this function, and then we'll also find the radius of convergence. All right, so let's start with that function. Let's just write it down again. So our function here is 1 over 1 minus 2x squared. All right, so if we could get rid of that squared, we'd be in good shape. We could use that special prototype that we've been looking at. How can we get rid of it? Well, we can actually get rid of it by integration. So that's what we're going to do. We're going to integrate this function. All right, so let's just do the integral. And to help us out, let's write it out. This is going to be one of our special k-forms. So let's just write it out, though. So we're going to do the integral. Let's use a negative exponent to help. So this will be raised to the -2. And when we do our integration here, we keep the inner term the same, the 1 minus 2x. We add 1 to the exponent, so it's going to take us up to -1. Take that new exponent, flip it, put it in front. And then this is one of our special k-forms. So we take that constant k that's in front of the x, and we flip that as well. So we're going to end up with 1 over -2. You could also do this with u substitution. And if we clean this up, we can take the -1/2, multiply it with the -1 here, and then write this back as a fraction. So if we do that, what do we end up with? Well, we're going to end up with +1/2 times 1 over 1 minus 2x. So I took the -1/2, moved it in the front, and multiplied it with the -1. And then we went back to a fraction. Now looking at this looks a whole bunch better. So this function, it's a brand new function, but this one is actually similar to that special prototype that we've looked at. 1 over 1 minus x. We do have a constant multiple in front. This 1/2 is just a constant multiple, but we've seen how to handle that. We can eventually, once we have the power series, we can multiply that in. All right, so now this is something that we can actually get our power series representation for. So that's what we're going to do. Let's get the power series. All right, so what do we have to do? Well, we've got to identify the R value. And this might take a little bit of work. We might have to, we need the 1 and we need the negative, which this one already has. But maybe on some more complicated examples, you might have to do that similar type manipulation in order to get it to have that correct format. But we've got the 1, we've got the minus, so we're ready to go. The R value here then is the 2x. So we want to identify the R value because, again, we're relating this back to a geometric series. So this is our R value here. And if we remember our prototype, this 1 over 1 minus x, what was the power series representation for that? Well, it was the sum of x raised to the power n, where n was going from 0 to infinity. So all we're going to do, we're going to use that same sigma notation here, that sigma form, but we're going to change that x to what this r value is. So wherever we see an x here, we're going to change that out with parentheses 2x. All right, so our power series will be the sum from n equals 0 to infinity of 2x raised to the n. And that's just the power series representation for this fraction here. But we also had that constant multiple in front, so let's throw that 1/2 in front here. So we've got that constant multiple floating around. All right, so this is pretty good, but we want to get this, want to write this in the correct power series format. So we want to separate all the constant terms from our actual power of x. So when we have multiplication going on inside an exponent, the exponent can distribute. So this can become 2 raised to the n times x raised to the n. And when we bring this 1/2 inside, we're going to be able to combine it with the 2 term. So let's see what that would look like. So first, let's actually break things up. So we'll have the 2 raised to the n times x raised to the n. And provided this series is convergent, we can distribute. So bringing the 1/2 inside is basically this is very similar to distribution over regular addition. So when we bring this in, now we're dividing by 2. So essentially, the 2 here is going to cancel off one of the copies of 2 in this exponential term. So we're going to end up with the sum from n equals 0 to infinity of 2 raised to the n minus 1 with times x raised to the power n. And this is our power series representation for that. We're doing pretty good. But we didn't want the power series representation for that. We wanted the power series representation for that. The original function with that squared around the denominator. So we have to go back. And how do we go back? Well, what did we do? We found the integral. We did integration. Well, what process undoes integration? And you're probably guessing right now. Differentiation. So we're going to differentiate. So we got to go back. So we're going to differentiate this power series here. And we've seen now how to actually differentiate a power series. It's actually very nice. We just differentiate the power function with power rule. All right, so again, we started with this function. We integrated, got a function that we could then find the power series representation for. And so to undo that initial integration that we did, we're differentiating to go back. All right, so let's do our derivative. And we're going to do power rule on that x to the n term. So how is this going to work? Well, we're going to bring the n down, put it in front. The 2 raised to the n minus 1 is just a constant, so that's just regular constant multiple stuff. Stays there. Keep x, and then subtract 1 from the exponent. And you can check the n equals 0 term, if we were to plug it in, is just going to be a constant. So we're not going to have an x there because x raised to the 0 is just going to be 1. And then the 2 raised to whatever is a constant. So for our starting index here, n equals 0, that term is just a constant. So when we differentiate, that term is going to disappear. It's going to differentiate to 0. So we can change our starting index then to n equals 1. And there we go. We've got it. This is It's bugging me. Hold on. That arrow was... Make this nice and symmetric looking. There we go. All right. So what do we have? Well, we have our power series representation now. So this is the one we wanted. All right, so we've answered the first part of this. We've got a power series representation for our function. So there it is. And the second part is we got to find the radius of convergence. So how do we find the radius of convergence? Well, we could do this a few ways. So this is a perfectly good power series. So to get the radius of convergence here, we could go back to our, abbreviate that, we could go back to our old method of doing the ratio test. Perfectly fine. So option 1, you could do ratio test on this brand new series. But in this case, we know that the power series we started with here was related to a geometric series. So we can actually find the radius of convergence for a little bit easier for this original power series that we started with. And the special thing about differentiation is it doesn't actually change the radius of convergence. So another option for how to get our radius of convergence is to find r for the power series we started with, the sum from n equals 0 to infinity of 2 raised to the n minus 1 times x raised to the n. Or, I guess actually, not even that one. Let's just do 2x raised to the n. This one we started with. And then note, differentiating and multiplying by a constant doesn't change the radius of convergence. So it's perfectly fine if you want to do ratio test on this one. Perfectly fine if you want to do the ratio test on that brand new series. Now that one's no longer geometric, so you can't just look at the r value in this case. It's no longer geometric. We've got this n here. But this one is. And so, yeah, you could do ratio test on this one. But what we're going to do is we're going to find the radius of convergence for this one. So what's our radius of convergence? And if we remember back, something that's, if it's a geometric series, we can kind of skip ahead a little bit. So let's figure out the radius of convergence. So we need, when we're dealing with a geometric series, we need the r value to be, the absolute value to be less than 1. Well, in this case, we found the r value to be 2x. So if we fill that in, we end up with the absolute value of 2x being less than 1. We can split up the absolute value. And so absolute value of just the 2, and then absolute value of just the x. Absolute value of 2 is positive, so we end up with 2 times the absolute value of x is less than 1. And then we can divide both sides of this by 2. So we get absolute value of x is less than 1/2. And once you get the absolute value of x, this term is the radius of convergence. But let's just double check that. So, you can't have any constants here. You got to be careful, any constant multiples. So it's still probably a good idea to just go through and get the interval. So if we write that as a double inequality, we end up with x between 1/2 and negative 1/2. And then our radius of convergence is half the width. And the width of this interval is 1. So you just got to be careful. This is really our radius of convergence. But if you had like 3 times x, you got to do something about that, the constant multiple. So if it was 3 times x, you'd have to do something about the 3. So just be careful. Usually good idea. Get it to this point with just the x in the middle so you can find your radius of convergence. All right, so that's it. We've got the radius of convergence for the power series we started with. So the radius of convergence for this one was 1/2. Multiplying by a constant doesn't change the radius of convergence. So this one also had a radius of convergence of 1/2. And we're just going to note that differentiation doesn't change the ROC. So differentiation works really nicely with power series. So that means the radius of convergence for the power series we're actually interested in is also 1/2. All right, so this is going to be these are kind of fun examples where you get to do a little bit of integration, differentiation. In class, we'll see another one where we have to start with differentiation. And so if we're starting with differentiation, well, to work backwards, we're going to integrate then. So these are always you're kind of undoing your previous work. All right, so we've got our answer. Here it is. Our power series and our radius of convergence. Good stuff. All right, so we'll see you in class. Bye-bye.